They're called Debye potential. So Mr. Debye must be very clever. He deserved the Nobel Prize. There are things like Debye-Heuker's method, and then there are things like Debye length, Debye potential. So he made quite a number of contributions to different areas.
What's the physical meaning of Debye potential?
Oh, it's a piloting potential that produces this field. I don't know what physical meaning to give it other than the fact that they satisfy the scalar Helmholtz equation. Or maybe in a little while later I will show that they are actually directly related to ER and HR. The Debye potential are directly related to the radial component of the E field and the H field. If you want to give physical meaning.
Don't we already know from this equation?
Not completely. But I'm going to manipulate this equation further. Okay, to simplify these two equations to give you a more direct relationship between the Debye potential and the radial component of the field. Okay. Who took my big table away? So I'm going to copy here instead of on my big table. Okay, let's go back to further simplifying this equation. Okay, we know that this has to be true, that Laplacian of pi plus k squared of pi must be equal to 0. But does anybody remember how to write the Laplacian in spherical coordinate system? No, right? Very difficult. So it's something like this. I don't remember either. And then there will be, let me look up my book, okay, it's my book. So make sure that I don't write the other components wrongly. It's in chapter 1 of my book. You're supposed to do the reading for that. So the other components are equal to this, okay, 1 over r squared sine theta partial theta sine theta partial theta pi. And then I have the other component, which is r squared sine squared theta partial squared partial phi squared pi plus k squared pi is equal to 0. Okay? But then if you assume that pi is of this form, pi is some radial function that I do not know yet. Let me call it little b. Okay? I do not know what this radial function is. But the azimuth, the spherical harmonics I know to be of this form. If you assume the pi to be something of this form, then all these things would simplify. Okay? It will simplify to something that looks like that, according to chapter 1 of my book. Then you can show that the simplification is that r plus k squared minus n plus 1 over r squared. In the textbook I call this k. Okay, let me just put the k back in there. Bn kr equal to 0. This is called the spherical Bessel equation. Okay, this is called the spherical Bessel equation.
Why have you assumed the solution to be of that form?
What is that?
Why have you assumed the solution to be of that form?
So because this is a spherically symmetric problem, and So you solve this problem by the separations of variables, and then there's the equation for the phi variable. Okay, you solve for a solution in the phi direction to be something of this form. So you let pi be a function of theta times a function of phi plus a function of r. This is called the method of separation of variables. And then because of this form, you assume that phi has to be of this form, minus m squared phi, right? That's the first thing you did. And then those are the e to the INPP solutions. And you plug that in, you can remove this term, and then you next assume that the Bessel function, no, not the Bessel function, the Legendre polynomials are the solution to the theta variables. And then after that, it's actually done in the chapter 1 of my book. Okay, let me write it down. Chapter 1 says that the Legendre's functions have to satisfy this equation. 1 over sine theta dd theta sine theta dd theta plus n plus 1 minus m squared over sine squared theta p n m cosine theta must be equal to 0. The Legendre's function satisfies that equation. Because of that, when you group terms together, all these things can be grouped together and show that B satisfies this equation by the separations of variables. Okay. You're supposed to know this, but I know it's very complicated material to remember. Okay, very complicated material to remember. I think this should be another currency system. Okay? But if you can't remember, just pull out a textbook like me. Okay? And copy it down, because I don't remember those things either. Too many things to remember in this world. But just remember the major concept here, which is the separation of variables. Break the equation in 3 equations and then solve them. Okay? And so your B equation becomes something like that, which means that actually you often find that this thing is written quite differently in different textbooks. Sometimes this thing is actually written this way. Sometimes this operator is written this way. Instead of saying this operator, sometimes it's written this way. And then you can use the chain rule and actually show that they're the same. Because if I write this out, this should be equal to 1 over r squared 2r ddr b plus r squared b squared dr squared, right? If I use a chain rule, that is equal to that. But then if you use the chain rule on that, they're the same. And if you have that form over there that you see in some textbooks, then this is the same as using the chain rule, 1 over r. Using the chain rule, this would give me 2 ddr bn plus r b squared dr squared bn. I believe the two are the same. Let me check. Yeah, they're the same as each other, right? So these two are the same as each other. Can you see? So sometimes in textbooks it's written like this, sometimes it's written like that. And don't get confused, they're the same thing. So I have it written like that, which means that you can use this fact to simplify the bipotential and say that this must be true also for the bipotential. If the bipotential has this spherical harmonics embedded in them, then it must be true that the bipotential part, the pi must be equal to minus k squared plus n plus 1 over r squared pi. This must be true. Okay? If the bipotential satisfies this equation, and if you go through all this algebra, this term here must be equal to that term over there. So you get a very nice relationship between HR and the bipotential. If I plug that in, then I should get what I should have inside my book. If I plug that in, then I can use that to simplify that thing. Okay, that will give me this expression over here. And then ER should be equal to 1 over I omega epsilon n plus 1 over R I E. Right? So you asked me what the physical meaning of the bipotential is. I can also say that the bipotentials are directly related to the R components of the E field and the H field for the TE wave and the TM wave. Okay, that's why I call this M, because this actually is related to the magnetic field. This thing is actually related to the electric field. So do you see how I get this, or you have a question as to how I get there? Essentially, I say that this must be true because of that, and if that is true, then if I use that in that, and these two terms cancel out, leaving me the n plus 1 term, and this must be true. Okay? Okay, having the radial component is not good enough, because what happens if you have an interface? You have HR, ER known here. You have also HR, ER known here. When you match boundary condition, you cannot match it with ER, HR. You need tangential E and tangential H. So we need E theta, E phi also in order to match boundary condition for this problem. So I like to derive E theta and E phi. And that actually is quite harrowing, right? Deriving HR already takes so much time, so deriving E theta and E phi also will take me some time. Okay, let me tell you the key essential. Okay, so I had that vector potential, and I like to tell you that HS is given by minus R pi E plus 1 over I omega mu 1 over R partial R R squared I M. Okay, this equation follows from the fact that H is equal to curl of R pi E plus 1 over I omega mu curl of R pi M. If I take the transverse component of that, I get that equation. Okay? And I do the same thing to my E field. If I take the transverse component of that, that gives me the quantity that looks like this. And if I don't like deriving things like this, I can just use duality and write things down like that. Okay? These are the transverse components. And you need these components to match boundary conditions at the interfaces. Okay? You want me to derive them, or you want? Yeah, just satisfied accepting them. You accepting them, right?
Is it on the homework?
You do it as a part of the homework. That's a good idea. That's fine.
No.
You do that as part of the homework, you have to go to some algebra.
I meant, is it already on the homework?
Well, it's one of the homeworks. Yeah, it's
The
one.
derivation you didn't do, or the derivation you did do?
This one I think is good exercise for you to do as a homework. I have it here, but I don't think I want to write it for you, right? So you do that as part of the homework. Okay. So this gives you all the machinery you need to solve the spherically layered medium problem. You solve tangential E, you solve for tangential H, and then you match boundary conditions. Okay? So when we have a spherically layered medium such as that one over there, without the machinery in place, then what we have to do is that, say if we have this problem,
Excuse me,
yes,
about P equals to curl F. F should be considered electric vector potential in analogy to a magnetic path.
right.
But I have never heard of it.
Oh, you go and look at Balani's book. I think he writes
Balani's
that.
book? Really?
Right.
Okay.
Balani's book. Yeah, nobody talks about it except for Balani. Okay.
He's my hero.
That's your hero. And then I think it's also taught in 520, right? Anybody's teacher is taking 520. So it's also been talked about there. Well, you never see this in physics book. Nobody talks about that. Because divergence of D is not truly zero. It's not
Then
zero.
why is it used?
It's used as an analogy. Because you do it for magnetic field, why don't we do it for electric field as well? Right? So it's done as an analogy.
Like the HR and the ER, there should be a summation like before them, right? And we need the boundary condition to define or to find the like factors between them. I mean from the HR and the ER in the middle.
Here.
Yeah. You have an N in the formula.
Yeah, assume that my Debye potential is of this form. In the circumferential direction is of that form.
Yeah, I know, but that's but should be a summation like a lot of this proof.
In general, it should be a summation, but I look at a particular mode.
Okay.
I just look at a particular mode, and that particular mode has this kind of variation in the theta and the phi direction. And you need only this mode to match boundary condition. I can show that you don't need the summations of modes to match boundary condition in spherical coordinate system. You just need one mode at a time. You can match boundary condition one mode at a time. You can put a summation there, making things more complete, but then you find that they are orthogonal to each other, and hence you can match boundary condition mode by mode. Okay, so we can address this problem one mode at a time, one spherical harmonic at a time. Okay. So, for instance, the general solution for the vector potential or the scalar potential in this problem then would be something of this form. The scalar potential have to be linear superposition of spherical Bessel function. This is not a cylindrical Bessel function. These are spherical Bessel functions satisfying this spherical Bessel equation. Okay, just be careful to distinguish the two. There is a cylindrical Bessel equation for cylindrical coordinate system. These are spherical Bessel function, and they usually denoted as lowercase j for the Bessel function. And then for the Hankel function, they are also denoted as lowercase. You can find them in Abramovich's and Stegen's book as well. They're also denoted as lowercase. And the most general solution is something of this form, where this is a 2 by 1 column vector. And then I can put the spherical harmonics on the outside. Okay, that is the most general solution for the pi sub e and pi sub m. And of course, you can have more than these two solutions to the spherical Bassel's equations. The others are the y-ends, sometimes written as this manner. Sometimes the Neumann, these are called the Neumann function of the spherical kind. Okay, sometimes they're written as that. And of course, you can also have the Hankel functions of the second kind. So altogether, you can have 5 kinds. But there are only 2 of them which are independent of each other, because this is a second order ODE. The second order stimuli will be a problem. Only 2 of them are independent. So you pick any 2 of the 5 and put it in here. That's good enough. Okay. But this has a meaning of an outgoing wave. This has a meaning of a standing wave, in my opinion. Okay? A meaning of a standing wave, and this is the most general solution. But those are proportional to the radial component of the electromagnetic field, and they're not sufficient to give you the data for matching boundary conditions. Okay, so you need the E theta and E field as well, and if I look at the ES, which is actually E theta and E phi, which you can obtain from that equation that I have just written down and not derived. Okay, and you can write them down in this manner. I over omega epsilon r partial square partial r partial theta r 1 over sine theta partial phi, and then I over omega epsilon 1 over sine theta partial square partial theta partial phi r, and then minus partial theta. Okay, then pi e pi m. So the transverse electric field can be written as such. And then the transverse magnetic field can also be written very similarly. Okay, but we cannot use duality principle to write this down anyhow. You can use duality principle sort of, but not to write this expression down. You can not write down this and then just use epsilon equals to minus mu, mu equals to minus epsilon, and then just write down. That's wrong. You have to be careful about some of the things, and then if you write it out correctly, these expressions should be something like that. And then this will be minus I over omega mu r. You see, this term becomes that term, but you have to switch them around because E theta becomes E phi and then pi e, and then the 2 got swapped around, so you cannot use duality principle directly, but indirectly. This term becomes that term, that term becomes that term. Theta partial square partial r partial phi r pi e pi m. Okay, so you have all this machinery that you can deploy and write down the transverse field components. And these expressions are difficult to write down, but it turns out that you can factorize them. You can factorize them as such that ES can be written as partial theta minus 1 over sine theta partial phi 1 over sine theta partial phi partial theta as I over omega epsilon 1 over r partial r 0 0 minus 1 pi e pi m. Okay, you can factorize them as such, and similarly you can do the same thing to hs, which can also be factorized with the same factor actually. Maybe I just write depot. Okay, depot over here. And then this factor is slightly different. It's sort of the dual of the above. And then minus 1, 0, pi e, pi m. Okay? This factorization is important. Okay? And so if you have this way of writing down the transverse field components, then what you can do now is to substitute this general expression you have for pi e and pi m into that. And because of this factorization, the theta derivatives and the phi derivatives only exist here. The radial derivatives only exist here. So I can write them as two separate factors. And I can write ES as being consisting of this theta and phi derivative operator operating on this. And if I let those things operate on that, that just gives me a matrix. A matrix which I call PNM theta phi, cosine of theta. Okay. And then e to the im phi. The e to the im phi is very simple. You just change the im here, and then you can put it outside. So that whole factor operating on this can be written as just a matrix times a scalar number. And then the rest of the thing operating on that just gives me something that looks like that. Okay. J, N, H, the matrix, right? If this thing operates on this thing over here, it will just give me a matrix KR dot with A. And then plus another matrix that corresponds to the Hankel function. Actually, these are the E's, okay, electric field type. KR dot with B. Okay? So ES would just look like that. Just imagine those differential operators operating on the pi's. This thing operating on a scalar number will just give me the matrix. And then if you work that out correctly, this will be the form of the E sub S. And then H of S will also be something of that form. You just plug it in. Into the IM phi. And then you will use this operator instead. This operator is not exactly that operator. It's kind of some sort of a dual and transpose of that operator. Of dual and the rows or column swap of that operator. So I will call this JNH KR dot A plus HNH KR dot B. Okay. So these are the general solutions for ES and HS. Any questions so far? I wouldn't write out the detail of this. You can look them up in the textbook. They are just derivative operator operating on those spherical Hankel functions. Okay. And the most important thing is that when you match boundary conditions, you will match this across an interface. The most important thing to prove is that these spherical harmonics are orthogonal to each other. If the ends and the m's are different, they will be orthogonal, so you can treat them mode by mode. Okay? You can match boundary conditions mode by mode. And it's proved in the textbook that these are orthogonal to each other. And furthermore, the orthogonality can be written down, but I can write it down for you. Okay, actually, I can write it out in a simplified form for you here. You can look at the detailed form in the textbook. It's quite clear that the m's are going to be orthogonal to each other. That's easily proved because the phi variation is always factored out. Okay, but it's not clear that the cosine theta form will be orthogonal to each other because they have been multiplied by this operator. But you can prove this to be true. This to be a constant delta and the constant is given in the textbook. Okay, the different n and n prime of this spherical harmonics are orthogonal to each other. And because of that, there should be an identity matrix over here because these are matrices. Okay. Because of that, you can consider the boundary conditions mode by mode, and more importantly, you can also show that the TE waves and the TM waves are decoupled at the boundary. Okay, that I'll show in a little while. Okay, the TE waves and the TM waves are actually decoupled. So we can do a simple problem with all the machinery that we have now. A simple problem of just say the radial wave propagating like this and then a transmitted wave. Just this simple problem. I have a wave that's outgoing, and then a reflected wave that's incoming, and then I have a transmitted wave in region 2. If I were to match boundary conditions, I can show you that the TE and TM wave are not coupled. So it's not that simple compared to the layered medium case. Layered medium case, we can show that quite easily. But for the spherically layered medium case, then you have to use this identity to prove that they are actually decoupled from each other. The boundary condition does not couple them. Okay, so that is very important. So, like in region 1, say if I call this region 1 and this region 2. In region 1, I can write down the solution as, let me just ignore the phi terms, okay? E1s has been equal to P and M cosine theta, Hn1, the matrix K1R. Okay, I'm writing down an outgoing wave in region 1, so this corresponds to this wave that is outgoing, and there will be a reflected wave generated. The reflected wave generated will be J, let me call this of E type, okay? JNE K1R, and then times another column vector B, but I'm going to bring them under the same unknown and call this R12, and then just put one column vector on the outside. So this is the most general solution for the field in region 1. Don't you believe so? Because A is known, because I'm going to assume that this outgoing wave is known with the known quantity A. The only unknown is the reflected wave, and that unknown I call R12 times A. So I'm introducing a reflection operator as a new unknown. Okay? This is the most general way to write down the solution in region 1. Any questions so far?
Professor, how come the reflected wave would be a J?
The J.
It's standing wave.
It has to be a standing wave because when the reflected wave comes to the origin, it gets reflected again. Okay? It gets reflected again so that it becomes a Bessel wave. You can write down a Henkel wave of the second kind. There's incoming, but when it reaches the origin, it will be reflected again. And then it will produce a Henkel wave of the first kind again. And these two always add up. And hence the reflected wave, including the reflection from the origin, always becomes a Bessel wave. Another way to saying that is that the reflected wave has to be regular at the origin. Another way of saying that is that these are two independent solutions to the Bessel's equation. They must be complete. Okay? They must be complete. And this reflected wave is non-singular at the origin. Say if I generate this with the line source at the origin. Okay, if I generate this first wave with the line source at the origin, the reflected wave will be regular at the origin. Okay, so I have to write it as a Bessel wave. And then I can write down H1s and mean very similar. But because they are generated with different operator, this Henkel functions of the matrix I'm called H, I think I call it H in my notes. Let me erase this now. Yes, it can be erased. Okay, that's the. And then I can write down the solution in region 2. Region 2 must be just an outgoing wave in region 2. And